This year alone, I've traveled to 6 continents, I've taken 56 planes, and I've emitted nearly 12 tons of CO2 equivalent from that alone. As I started having a hard time looking my kids in the eye and telling them I was doing all of that for good, I decided to compensate for my carbon emissions by planting trees. We've had that dead tree in the garden for 2 years now, so I could totally uproot it and replace it with a couple of new ones to balance out my travels, right? So I looked up what gargantuan amount of CO2 a tree could absorb in a year to figure out how much I should plant in my garden, and oh, I have a problem. During its first 20 years, the average tree absorbs an average of 10 kilograms of CO2 per year. So I would need to install 1,170 of them. You know what, buddy? For now you're staying. I got another idea. Indeed, I have a superpower. I'm a water professional. What's that to do with my CO2 emissions? Well, actually, the water sector is also a potent CO2 emitter. As a ballpark figure, its emissions are of a very similar magnitude as the aviation sector. Yet when you're stepping in a plane in 2023, it's hard to ignore that travel has implications for greenhouse gas emissions. But did you ever think of that while pouring a glass of water, flushing the toilet, or cleaning out your septic tank? Sorry, I don't have a septic tank, so the closest I could think of was emptying my spam folder. Today, I want to explore 5 paths a water professional can follow to reduce the water sector's carbon impacts. I then run the calculation of how much savings one single water pro could generate with each of them, and we'll see at the end if I actually mitigated my own emissions for this year, and if not, what I shall change to achieve it. But first, we need to understand where the water sector's emissions come from. According to Global Water Intelligence, the water sector emits 845 billion tons of CO2 equivalent per year, almost equally distributed across drinking water, wastewater, and on-site sanitation. On the drinking water end, it's almost one-to-one an energy issue. Pumping raw water, treating it or desalinating it, and then distributing it is energy intensive and emits 323 million tons of CO2 a year. For wastewater, the picture is a bit more complex because within the 256 billion tons of CO2 equivalent it emits, you have a good chunk of energy impacts both on the sewage network and within the wastewater treatment plant, but you also have methane and nitrous oxide emissions within that plant, which have quite some effect. That influence is even much higher if you look at the short-term effects, as methane has 80 times the global warming potential of CO2 over 20 years. Finally, on-site sanitation emissions are almost exclusively a methane story, for a total of 266 million tons of CO2 equivalent per year. And it is a concerning story for the exact reason I just mentioned. Methane is worse in the short term than CO2. So what can we do as water professionals to reduce those emissions? Let's start with idea number 1, leak reduction. An estimated 126 billion cubic meters of drinking water is lost on the world's water networks every year. That's a huge waste of the water resource, but it's also a big energy hit. Indeed, it means you have to pump up 126 billion cubic meters of raw water, treat it to drinking water standards, and then pump it again along water networks, only for that water to kind of vanish and never reach people's home. That water is sometimes even desalinated in the first place, which means it is even more energy intensive. So if you reduce the leaks, you also reduce that waste of energy, and in turn you reduce the carbon impact. Now, to reduce network leaks, you could pick several approaches, and often all of them in combination. I could have gone for leak detection or network modeling, but for today I'll go with pressure management. Sure, that won't stop your network from leaking, but it will make it leak slower as there will be less pressure in it. Plus, it's a quite affordable approach and it offers a great speed of deployment. Welcome side effect, pressure management also reduces the stress on parts of your network which might not be leaking today, but might in the future, hence prolonging the lifetime of network sections you anyways didn't have the budget to replace. Don't get me wrong, I'm not opposing different leak reduction approaches. Ideally, we'd run all of them. I'm just saying that for today's exercise, I'm going to go with pressure management. The city I'd like to help, let's pick my hometown, Colmar, has approximately a population of 100,000 and an additional 100,000 population equivalent of industrial water users. I'll assume it has the European average leak rate of 26%, so it leaks 3.1 million cubic meters of drinking water annually, taking an emission rate of 0.137 kilogram per cubic meter as determined by the University of Bucharest. These leaks have an impact of 429 tons of CO2 equivalent per year. But how much can I reduce them by managing the pressure? That gets a bit techy, so I've asked my colleague Olivier Narbet for some help. Following Bernoulli's principle, flow evolves according to the square root of pressure difference. In case you need it, I've left a glass of water and some paracetamol right here. Just help yourself. So let's assume a pressure reduction of 25% across the network. That gives us a pressure difference of 0.75, the square root of which is 0.87. So my new water losses will be 3.1 million cubic meters times 0.87, which makes 2.7 million cubic meters and hence a saving of 420,000 cubic meters per year. Translated into carbon impact, I would now be saving 57 tons of CO2 per year, and my entire system having a lifetime expectancy of 20 years, I'd be saving 1,150 tons of CO2. So if my job as a water professional was to engineer, sell, install and maintain a pressure management system for a low to mid-sized city like Colmar, I would have a positive carbon impact on the world as long as doing so doesn't cost me more than 1,150 tons of CO2 over the next 20 years. Assuming 4 in-person meetups before signing the contract, 4 additional visits to roll out the system, and then 1 maintenance visit every 5 years, that makes for 12 visits to the job site, back and forth. So with a capital of 1,150 tons of CO2 to burn before reaching break-even, I could be living on the absolute other side of Earth, traveling by plane and in first class all the time, and still barely burning 15% of my carbon budget. And if that were my job, I would have a positive carbon impact even in a crazy travel year like this one. So it's maybe worth asking, Olivier, would you let me have your job? No? Shit.
I'm a vulgar man.
So I'll have to move to my second idea, a pretty close one actually, smart pumps. 90% of the energy that's consumed on water and wastewater networks is actually consumed in pumps. And even though a 2023 pump might not be spectacularly more efficient than a 2022 pump, if you bear in mind the super low renewal rate of networks, you can easily figure out that many pieces of hardware out there are a bit outdated.
Okay, well, anything in here is outdated and unfit for use.
Now the keyword in smart pump is actually not pump, but smart. A word that's overused, I know. Let me explain. What could make a pump smart? Well, it's a combination of things. For instance, your city is probably not fully flat, so by using the geography and knowing where people will use water and when, you can schedule your pump use to optimize energy consumption, bring water where people are and when they are there, and use gravity as much as possible. So, in fact, smart pumping is not just a pump story, but also a network modeling exercise and a digital connection of your various assets. Along the same lines, companies like Grundfos, Xylem, Veolia or Suez all market different shades of machine learning that also enable preventive maintenance. I know, one more buzzword, but a malfunctioning pump is also consuming more, so you'd better always have them in good health. Bearing in mind that a pump will cost you about 20 times more in operation costs than it does in investment costs. Add a little bit of variable frequency drives to round it off, and you get that there's energy savings to find in pumping. But how much?
Good question.
In their net zero white paper, Xylem mentions intelligent pumping systems that can cut energy use by up to 70%.
That's a lot.
I have a hell of respect for Austin Alexander, their VP of Sustainability, but I'd still not take 70% as the ballpark figure of what's reasonable to await from a smart pumping system. Later in the paper, they get a bit more measured and mention more than 25%. Cross-comparing a bunch of studies, it sounds like the right magnitude of savings to expect. Let's say I stay on the safe side and assume a 20% reduction for the next steps. But how much carbon would I save with that cut on energy? Let's get back to Excel and to my fictional example of Colmar. I used my secret archive of projects to estimate the energy spent on pumping for my 200,000 population equivalent case study.
What did you expect?
And that's about 2 million kilowatt-hour over the year. In their white paper, Xylem takes a CO2 equivalent factor for energy generation of 0.71 kilogram of CO2 per kilowatt-hour. That's the ratio for all fired plants. Somebody wants to sell pumps, right? I could have gone for even worse though. Think of Germany and their coal-fired power plants, but let me be reasonable and go for the less CO2 intensive gas-fired. That makes a yearly CO2 emissions of 906 tons. Now, if I cut 20% of that, that's 181 tons of CO2 per year. That's about 3 times higher savings than with my pressure management idea, so it's safe to say it would widely cover my travels. Once again, thumbs up. The superpowers of water professionals would also prove effective in smart pumping. Yet, that's still not my job. So let me move to my idea number 3, biogas enhancement. Do you know what that is? It's a piece of titanium, and the thing that's running out to that extreme might surprise you. It's actually wastewater sludge. Sludge is a byproduct of the activated sludge wastewater treatment process that's widely used as secondary treatment everywhere around the world. It's a waste you'll have to dispose of and something you'll have to concentrate and dry. But it's also energy if you're able to tap into it. One pretty common way to do so is to digest it in order to produce biogas, which you can then use as fuel to heat your offices and power your plant through cogeneration. Some even manage to produce a little surplus, which they then refine into biomethane and inject into the gas network. All in all, that's a carbon saving that a wastewater treatment plant can generate, as this carbon neutral biogas one-to-one replaces fossil fuels. And it comes with welcome side effects. All the methane collected during the anaerobic digestion will no longer be available to be directly released during the following sludge management steps, and the sludge itself will have a lower volume, reducing the energy needs for these said next steps. In a nutshell, biogas production is good, and the more you produce, the better. And that's where pieces of technology like this one enter into play. When I was a water engineering student about to graduate, my thesis project was to find ways to enhance biogas production by 30% on a 60,000 population equivalent wastewater treatment plant in order to produce 70 kilowatts of energy 24/7. Okay, and I also did things like that. But back to my story. The way I tried to do that was with a system featuring 5 heads like this one that were producing ultrasounds in a shock treatment for sludge before getting sent to the digester. Now, the reason why that head is in my hands 12 years later and not in the plant is that we didn't quite achieve the 30% target. It was working, but it was more in the 10 to 15% ballpark figure. But in the meantime, companies like Cambi, Tomorrow Water, or Naihu Store Industries market another technology, the thermal hydrolysis process, or THP, that actually achieves the 30% enhancement, as Cambi's CEO confirmed me. So let's apply this to our 200,000 population equivalent case study. With regular anaerobic digestion, that plant shall be able to produce about 320,000 cubic meters of biogas per year. Let's assume we now come in and spice things up with a THP process, bringing an additional 30% production capacity. That makes 96,000 cubic meters of biogas per year. Producing 1 kilowatt hour of energy requires 0.21 cubic meter of biogas, so if you use that additional biogas as a one-to-one replacement for natural gas, you're now producing about 450,000 kilowatt hour of electricity per year, which in turn represents a yearly saving of 196 tons of CO2 equivalent. And this, once again, would cover my CO2 impact from this year's travels. It would even cover it 16 times. But yeah, I'm holding that probe head in my hand and not selling or installing THP processes, so let's move on to my next idea, aeration optimization. That one is interesting and tricky. I mentioned the activated sludge process just 2 minutes ago, and that's the one we'll try to optimize now. But why should it be optimized? Well, simply because that's a treatment step that's super energy intensive. It looks like a brown jacuzzi for a reason. You've got huge aeration lines that send compressed air into the reaction tanks, and these compressors are responsible for 50, 60, and sometimes even 70% of the energy consumption of a wastewater treatment plant. There's probably already room to optimize on the hardware end of that equipment. That's something we discussed with Ricardo Verbein when we both joined the IoT Use Case podcast earlier this year. Yeah, crazy, right? I was a guest, not the host. His company, Xylem, has interesting solutions in that field. But there's also an operation layer that I'd like to focus on here. A bit too often, a plant's aeration is run quite erratically. When your treatment performance is good, you shut down aeration to save energy. And then when performance drops, you enter turbo mode to bring everything back on track. The bottom line is that those compressors are very seldom used in their ideal operation range, which leads to huge inefficiencies. The thing is that this operation is a complex equation. Wastewater's load evolves by the minute, flow is also a moving target, same with meteorological conditions, and you're dealing with biology, so there's no such thing as on and off. That's the kind of riddle that the human brain has a hard time solving efficiently 24/7, but that's what machine learning and artificial intelligence call a cool breakfast.
Feed me. Charge me.
That's how companies like Pure Control, Gradient, or Penny, to name just a few shiny ones, are offering AI solutions to cut your energy bill by at least 20%. But, as I mentioned from the beginning, this part is tricky, because in the case of the activated sludge process, energy is not fully the right North Star metric. you have to zoom out to be even more holistic in your approach to greenhouse gas emissions because of another player, nitrous oxide. N2O has 273 times the global warming potential of CO2, and its generation actually increases when you're too optimal with energy consumption. Something we discussed with Maria Manidaki on the podcast. My podcast this time? I was back to being a host. Now the good news is that this additional parameter might be one more headache for a human brain, but is still pretty manageable for AI and neural networks. I've heard, for instance, from Pure Control at the recent Aquatech that they were on the verge of having N2O as a standard module in their offering in partnership with Cobalt Water. Sure, here one way to potentially measure your impact as a water professional would be to follow track with my previous ideas and evaluate how much CO2 we're saving with a 20% energy cut. But maybe more interestingly, when we consider that 32% of the greenhouse gas emissions from wastewater treatment come from nitrous oxide, and we factor in that these emissions could be cut by whether optimizing the processes or switching the core of the technology from activated sludge to, for instance, membrane aerated biofilm reactors, we have an opportunity here to simply have the most potent impact of all ideas so far. So, if you're in operation optimization, MABR technologies, or even fancier approaches like AquaCycle or Cambi innovations, it looks like you could even coin the term carbon hero. But when it comes to me, well, that's still not what I do, so it still doesn't mitigate my carbon emissions. Yet I have good hope for my fifth and last idea, influencing policies and incentives through advocacy. I know what you think, that's cheating, but let me a chance to explain. The water sector is a highly regulated one. Yes, Captain Obvious is back. The consequence is that it's pretty hard to move outside of regulations. If regulation doesn't push for something, that said something doesn't happen. Greenhouse gas emissions are obviously on the world's agenda. But is the water sector at the top of the list? Not at all. As I said in the beginning, you worry about your flights, not your flush. Now, yes, there's a drive within the industry to get things done. Water UK has set an ambitious net zero goal for 2030, and all major Australian utilities have joined a twin movement down under. On GWI's count, 479 utilities have set net zero targets, which is to be contrasted by the fact that only 82 have really set a date for that target, that date also being 2050. But a drive is not enough. All the solutions I've brainstormed today and all the other ones like heat exchangers, biochar, hydrogen production, all the shades of fuel cells, and all the ones you might suggest me to look into in the comments will have an investment cost. I believe most of them will also have a return on investment, but someone still needs to pay up front, and utilities and their struggling budgets will have it hard to justify the big buck. A sad example of that is what happened to Energia at their Rialto plant. With an enforced California regulation, they had a business case and an incredibly positive carbon impact. With the postponement of the regulation, they had a bankruptcy and a tumbling stock price. Beyond just regulations, we also need to craft the right incentives. Here's what I mean by that. Let's imagine we set CO2 targets and CO2 only. One extreme way to achieve the target would be to let wastewater rot away. That doesn't require energy, but beyond the health and environmental hazard, it will massively emit methane and nitrous oxide, which we know to be even worse. Wrong incentive, wrong result. Kind of an Aston Martin Signet.
What's this saying?
Of course, my rotting wastewater example is extreme, but my Aston Martin Signet analogy is not fully out of this world. There as well, the regulator focused on CO2 only and the market got creative. Energy is important, but cutting N2O and measuring CH4 correctly is probably even more so. Along the same lines, if we're serious about greenhouse gas, it should become a decision criterion when engineering a new plant. Do you really need desalination when you could be reusing wastewater for half the carbon impact? Do you really want to go for a brand new activated sludge plant when an MABR would make your water fitter for reuse while cutting the nitrous oxide emissions in half? As often, to get a glimpse of the future, you look at the good pupils. Denmark is drafting N2O emission regulations by 2025, and it comes with a wealth of welcome side effects from water reuse to ammonia recovery. So what do you think? Does advocacy count as a positive carbon impact? You'll tell me. What's for sure is that it's harder to quantify. I can't really fit it in my Excel table and put nice numbers that would make me look good.
Shame. Shame.
I wouldn't pretend that because you're a few hundred to watch me, thank you for that, and if it's your first time here, make sure to subscribe. I can wash off my 12 tons of 2023 emissions. Creating this content is my way to offset these emissions. But I'm not creating the emissions because of the content. I'm traveling because I have a full-time job as business development manager for water and lithium topics for GF piping systems, which I would believe to also have a positive carbon impact. Call me, we'll discuss it. And then my little advocacy on evenings and weekends helps mitigate my impact. The open reflection for me, though, is what to do with conferences. You could be on the road twice a week, all year long, only to attend conferences. And that's for sure something I'd like to avoid. So I'll fight hard to keep it under control and only have the kind of good surprise I had in Amsterdam this year. If you want to check out my feedback from this year's Aquatech, it's right here, and I'll see you next time.